Hello there, and welcome to Sleepy Science Vault. There is something profoundly humbling about looking up at the night sky and realizing that everything you can see, every star, every galaxy, every faint smear of light stretching across the dark, represents only a small fraction of what is actually out there. Most of the universe is hidden from us. Not hidden in distant corners of space, or buried beneath layers of cosmic dust, but hidden in plain sight, woven through the fabric of everything, unseen and almost completely silent. This is the story of dark matter. Dark matter does not glow. It does not shine. It does not emit radio waves, or infrared warmth, or the faintest trace of X-ray light. Every tool humanity has ever built to detect light, and we have built extraordinary ones, returns nothing when aimed at it. It simply refuses to be seen. And yet, scientists are certain it exists. That certainty comes not from seeing dark matter directly, but from watching what it does. Gravity is the messenger here. Across the universe, galaxies spin faster than they should. Clusters of galaxies bend light more sharply than their visible mass could ever account for. Something is adding weight to the equation, something enormous, and it isn't anything we can point a telescope at. The idea was first taken seriously when astronomers noticed a troubling mismatch. The gravity holding certain galaxies and galactic clusters together was simply too strong. There wasn't enough visible matter, not nearly enough, to explain the forces at work. Something unseen had to be there, pulling, holding, shaping. Over time, that unseen something earned a name. Dark matter. Not dark because it is sinister or strange, but dark simply because it gives off no light at all. It is sometimes described as the invisible glue of the cosmos, and that is a surprisingly accurate image. Without it, galaxies as we know them likely could not hold their shape. The large-scale structure of the universe, those vast cosmic webs of filaments and voids, probably could not have formed the way it did. Dark matter was there in the early universe, quietly providing the gravitational scaffolding that ordinary matter eventually gathered around. And there is a lot of it. When scientists map out the total content of the universe, all its mass, all its energy, visible matter, everything made of atoms, everything you have ever touched or seen or measured, accounts for only about 5%. Dark energy, the mysterious force driving the universe's expansion, accounts for roughly 68%. Dark matter fills in much of what remains. About 27% of the universe's total mass energy content is dark matter. More than 5 times the amount of ordinary matter. It outweighs the visible universe by a staggering margin, and we still don't know what it actually is. It is worth pausing on that. 27% of everything. And we cannot see it, touch it, or detect it with any instrument we currently have. Dark matter is also not the same thing as dark energy, though the two are often confused. Dark energy is what's pushing the universe apart, accelerating its expansion in ways that still puzzle physicists deeply. Dark matter, by contrast, pulls. It gravitates. It clusters. It behaves, in that sense, like matter should, just invisibly. What makes dark matter especially strange is how little it seems to care about the world around it. It barely interacts with ordinary matter at all. Not through light, not through electromagnetic force, not through the chemical bonds that hold atoms together. It moves through walls, through planets, through human bodies, through entire galaxies, with almost no resistance whatsoever. Right now, as you rest here quietly, dark matter is passing through you. Through the walls around you. Through the earth beneath you. Billions of particles, if that is even what they are, flowing through everything without leaving the faintest trace. It is one of the strangest ideas in all of science. And it is almost certainly true. The universe is mostly made of something we cannot see, do not fully understand, and can only infer from the shadows it casts on the things we can observe. There is something quietly beautiful about that, a reminder that reality is far deeper and stranger than it first appears. And we are only just beginning to understand it. For all the certainty that surrounds dark matter, the mathematical models, the gravitational evidence, the decades of careful observation, there is one striking fact that tends to stop people in their tracks. We have never directly detected a single dark matter particle. Not once. Not even a whisper of a signal that could be cleanly attributed to one. Despite some of the most sensitive detectors ever built, buried deep underground to shield them from interference, despite particle accelerators pushing the boundaries of known physics, despite space-based observatories scanning the sky in every wavelength imaginable, the particle itself remains elusive. This is perhaps the most extraordinary tension in modern science. We are more confident that dark matter exists than we are about many things we can detect directly. The gravitational evidence is overwhelming. The theoretical framework is solid. And yet the fundamental nature of dark matter, what it actually is, at the level of particles and forces, remains completely unknown. It is one of the greatest open questions in all of physics. Not a minor puzzle at the edges of our understanding, but a central, unavoidable mystery sitting right at the heart of our picture of the universe. And the story of how we arrived here is a remarkable one. It begins, as so many scientific discoveries do, not with a celebrated announcement, but with a nagging problem that most people initially chose to ignore. In 1933, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a vast collection of galaxies roughly 300 million light-years from Earth. He was measuring how fast the galaxies within the cluster were moving relative to one another, and what he found troubled him deeply. They were moving far too fast. In any gravitationally bound system, there is a relationship between the total mass present and the speeds at which objects move within it. Too fast, and the system should fly apart. The galaxies Zwicky was observing were moving at speeds that should have sent them scattering in all directions long ago. And yet the cluster held together, stable and intact. Zwicky calculated how much mass would be needed to keep everything bound, and then compared that to the mass he could actually see. The numbers were wildly different. The visible galaxies accounted for only a small fraction of the gravity required. He proposed that the cluster must contain vast quantities of unseen matter that contributed gravitational pull without contributing any light. He called it Dunkel Materie, dark matter. The scientific community was largely unconvinced. Zwicky was known for being difficult and contrarian, and the idea seemed too strange, too speculative. It was quietly set aside. It would be decades before the evidence became impossible to dismiss. The person who changed everything was an American astronomer named Vera Rubin. Working in the 1970s alongside her colleague Kent Ford, Rubin was studying the rotation of spiral galaxies, measuring how fast stars at different distances from the galactic center were orbiting around it. The expectation, based on the same logic that governs our solar system, was straightforward. Stars closer to the dense, bright center of a galaxy should orbit quickly, pulled by all that concentrated mass. Stars farther out, in the sparse outer reaches where visible matter thins to almost nothing, should orbit more slowly, just as the outer planets of our solar system move more slowly than the inner ones. What Rubin found was nothing like that. The outer stars were moving just as fast as the inner ones. Some were even faster than expected. The rotation curves of galaxies, instead of falling off gently with distance the way theory predicted, stayed stubbornly flat. No matter how far out you looked, the orbital speed simply refused to drop. There was only one reasonable explanation. The visible matter, the stars, the gas, the dust, was not the whole story. Something else had to be there, spread throughout the galaxy and well beyond its visible edges, contributing mass and therefore gravity, keeping those outer stars locked in their orbits rather than drifting away. Vera Rubin had found the evidence that Zwicky's idea had been waiting for. And this time, the scientific community listened. What emerged from her work was a new picture of how galaxies are structured. Galaxies, it turned out, are not simply the bright spirals and ellipses we see in photographs. They are embedded in something far larger, vast, invisible regions of dark matter that extend far beyond the visible disk of stars and gas, enveloping entire galaxies in what scientists now call dark matter halos. These halos are not small. They can extend hundreds of thousands of light years in every direction, dwarfing the visible galaxy at their center. The Milky Way, for example, sits within a dark matter halo that may be 10 times larger in diameter than the galaxy itself. The dark matter there is not concentrated at the center, the way most visible matter is. It is distributed across an enormous volume of space, diffuse and vast and completely invisible. This distribution matters enormously for how galaxies form and evolve. In the early universe, it was these dark matter halos that first began to collapse under gravity, forming the gravitational wells into which ordinary matter eventually flowed, slowly building up into the stars and galaxies we see today. Without the dark matter halos providing that initial gravitational structure, the universe might look very different. Galaxies might never have formed at all. But confirming the existence of something invisible requires more than just watching stars orbit. Scientists needed other ways to test the idea, other lines of evidence that could be gathered and compared. One of the most beautiful came from light itself. When light travels across the universe, it does not always travel in a straight line. Mass-warped spacetime and curved spacetime bends the path of light passing through it. This effect, predicted by Einstein's general theory of relativity, is called gravitational lensing, and it has become one of the most powerful tools astronomers have for mapping matter in the universe, including matter that cannot be seen. When a massive object, a galaxy, a cluster of galaxies, or a concentration of dark matter, sits between us and something more distant, it acts like a lens. The light from the background object is bent around it, sometimes creating multiple images, arcs, or rings. By carefully analyzing the degree of this bending, scientists can calculate exactly how much mass must be present in the foreground, regardless of whether that mass is visible or not. And what gravitational lensing consistently shows is that the mass inferred from the bending of light is far greater than the mass accounted for by visible matter alone. The invisible component is there, quietly bending light across billions of light years, giving itself away through Einstein's geometry even as it refuses to emit a single photon. This technique has mapped dark matter across the entire large-scale structure of the universe, tracing its distribution through vast cosmic filaments, enormous galaxy clusters, and the deep empty spaces between them. It has revealed a universe shaped, at its largest scales, primarily by something we cannot see. Then there is the bullet cluster. If any single observation captures the power of the evidence for dark matter, it is this one. The bullet cluster is the result of two massive galaxy clusters that collided roughly 150 million years ago, a cosmic collision of almost unimaginable scale, involving trillions of stars and vast clouds of hot gas. When the two clusters passed through each other, different components behaved differently. The stars in each cluster, despite their enormous numbers, are so sparsely distributed that they pass through the collision largely without interacting. Like two swarms of bees passing through each other. But the hot gas, which makes up the majority of the ordinary matter in galaxy clusters, is not so fortunate. Gas interacts with gas. It collides, slows down, heats up, and gets left behind. The gas from both clusters piled up in the middle of the collision zone, glowing brightly in X-ray light, forming the distinctive bullet shape that gives the cluster its name. Now here's where it becomes extraordinary. Scientists used gravitational lensing to map the total mass distribution of the bullet cluster, including any dark matter that might be present. And what they found was that the majority of the mass was not in the middle, where the gas had piled up. It was out ahead, on either side, in the regions where the stars and dark matter halos had continued moving forward through the collision. The dark matter halos of the two clusters had passed through each other almost without interacting, exactly the way you would expect from something that barely engages with ordinary matter. The gas slammed together and stopped. The dark matter sailed straight through. This is one of the most direct pieces of evidence ever gathered that dark matter is a real, physical substance separate from ordinary matter, not a modification of our understanding of gravity, not an artifact of incomplete data, but something genuinely there, behaving according to its own rules. The bullet cluster is hard to look at and walk away unconvinced. So we arrive at the present moment with this strange, layered picture of the universe. Built up over nearly a century of careful observation, from Zwicky's troubling calculations in the 1930s to Vera Rubin's rotation curves to gravitational lensing maps to the collision dynamics of the bullet cluster. Each piece of evidence pointing in the same direction. Each one deepening the same essential mystery. dark matter is real. It surrounds and permeates the visible universe. It shaped the galaxies we live in. It bends light across billions of light years of space. It passes through ordinary matter as though it barely notices it is there. And we still do not know what it is. That question, the deepest one, remains open. Patient and quiet, like dark matter itself, waiting to be answered. Long before the first star ever ignited, long before the first atom of hydrogen collapsed into the first fragile knot of light, the universe was already being shaped by something invisible. The story of how the cosmos came to look the way it does today is, in many ways, the story of dark matter. Not because dark matter is the only actor in this vast drama, but because it was the first. It moved before ordinary matter could. It clustered before stars had any reason to form. It laid the groundwork for nearly everything that followed. To understand how remarkable this is, it helps to travel back, not just years or centuries, but billions of years, to a universe that would be almost unrecognizable to us now. In the early universe, the cosmos was extraordinarily smooth. Matter was distributed nearly uniformly across space, with only the faintest, almost imperceptible variations in density from one region to the next. These tiny fluctuations, smaller than a fraction of a percent, were the seeds of everything. Every galaxy, every cluster, every vast structure in the universe today grew from those delicate early differences. But ordinary matter, in those early moments, had a problem. It was coupled to radiation. The early universe was so hot and dense that light and matter were locked together, constantly interacting, and this constant pressure from photons prevented ordinary matter from clumping freely under gravity. Whenever ordinary matter tried to collapse into a denser region, radiation pushed back against it, smoothing things out again. Dark matter did not have this problem. Because dark matter does not interact with light, it was free from that radiative pressure entirely. While ordinary matter was being held in place, kept smooth and uniform by the constant push and pull of photons, dark matter was already responding purely to gravity. It was already beginning to clump. Already beginning to gather into the first faint concentrations that would eventually grow into something much larger. This is why scientists think dark matter may have begun clumping significantly earlier than ordinary matter did. It had a head start. And that head start mattered enormously. As dark matter slowly gathered under its own gravity over millions of years, it built up regions of higher density, shallow gravitational wells scattered across the expanding universe. When ordinary matter finally decoupled from radiation, when the universe cooled enough that light and matter could go their separate ways, ordinary matter was suddenly free to move. And it flowed, naturally and inevitably, toward the places where gravity was already strongest. Toward the dark matter. In this way, dark matter didn't just coexist with the formation of galaxies and stars. It invited them into existence. It provided the structure, the gravitational scaffolding, that ordinary matter needed to begin assembling itself into something coherent. Without that scaffolding, the process of galaxy formation would have been slower, more diffuse, less organized. Some astronomers believe that stars and galaxies formed earlier in cosmic history than they otherwise would have, precisely because dark matter had already done the hard work of concentrating gravity into useful places. The universe was, in a sense, prepared for them. What emerged from this process, over hundreds of millions and then billions of years, was one of the most spectacular structures in nature, the cosmic web. When you look at large-scale maps of the universe, the kind assembled from surveys of millions of galaxies, what you see is not a random scatter of points. You see a network. Vast filaments of matter stretching across hundreds of millions of light years, connecting at dense nodes where galaxy clusters gather. Between these filaments lie enormous empty spaces, cosmic voids where almost nothing resides. The overall pattern looks, with a certain poetic accuracy, like a web, or perhaps like the delicate branching structure of neurons in a brain. This cosmic web is not made primarily of visible matter. It is made primarily of dark matter. The filaments are dark matter filaments. The dense nodes are dark matter halos clustering together. The visible galaxies that illuminate this structure are, in a sense, tracers, bright markers sitting within a far larger, invisible architecture that dark matter built. Gas and visible matter follow. Galaxies tend to cluster in the same regions where dark matter clusters, drawn there by gravity, settling into the structures that dark matter defined. Scientists have found consistently that dark matter, gas, and galaxies cluster together in the same regions of space, a tight collocation that reflects how deeply intertwined their histories are. The visible universe and the invisible one occupy the same places because one was built inside the framework of the other. There is something quietly astonishing about this picture. Every galaxy you have ever seen in a photograph, every cluster, every grand spiral arm lit up with stars, all of it is embedded in a universe-spanning structure that you cannot photograph, cannot directly observe, and could not have predicted without decades of careful mathematics and observation. Dark matter shaped galaxies not just at their formation, but throughout their evolution. The size of a dark matter halo influences how large a galaxy grows. The distribution of dark matter within and around a galaxy affects how its gas flows, how its star formation proceeds, how it merges with neighbors over cosmic time. Galaxies are not simply islands of stars floating freely in space. They are the visible cores of dark matter structures, and those structures have guided their development from the very beginning. This relationship becomes especially interesting when you look at the smallest galaxies in the universe, the dwarf galaxies. Dwarf galaxies are exactly what they sound like: small, faint, often irregularly shaped galaxies containing far fewer stars than the Milky Way or Andromeda. Some contain only a few million stars, compared to the hundreds of billions in a galaxy like our own. They are easy to overlook. But for scientists studying dark matter, they are extraordinarily valuable. The reason comes down to ratios. In large galaxies, ordinary matter, stars, gas, dust, makes up a substantial fraction of the total mass. The dark matter is dominant, but the visible matter is at least a significant presence. In dwarf galaxies, particularly the faintest and most isolated ones, visible matter is almost negligible. The ratio of dark matter to ordinary matter can be extreme, sometimes overwhelmingly so. These are systems that are nearly pure dark matter, with just enough stars sprinkled in to be detectable at all. This makes them ideal laboratories. When you study the motions of stars in a dwarf galaxy, how fast they move, in what directions, with what spread of velocities, you are essentially reading off the properties of the dark matter halo almost directly, with very little contamination from the effects of visible matter. Some astronomers consider dwarf galaxies among the most important objects in the sky for testing ideas about what dark matter is and how it behaves. There is also a deeper puzzle lurking here. Theoretical models of dark matter predict that the universe should contain far more small dwarf galaxies than we actually observe. Around large galaxies like the Milky Way, simulations suggest there should be hundreds or even thousands of small dark matter halos, each capable of hosting a dwarf galaxy. We see far fewer than that. Whether this discrepancy reflects gaps in our understanding of dark matter, or whether it reflects the effects of stellar processes that disrupt or suppress galaxy formation in small halos, is still actively debated. It is one of several places where the theoretical picture and the observed universe don't quite line up, and where the real answers, when they come, will likely teach us something important. Then there is the question of what dark matter does at the very centers of galaxies, specifically in relation to the supermassive black holes that reside there. Nearly every large galaxy appears to host a supermassive black hole at its center, objects with masses ranging from millions to billions of times the mass of our Sun. How these black holes formed and grew is its own deep mystery, but dark matter may be part of the story. Some researchers have proposed that as dark matter halos collapsed in the early universe, concentrations of dark matter at galactic centers could have provided additional gravitational fuel for the growth of these black holes, helping them reach their enormous masses more quickly. Others have explored whether the density of dark matter near a galactic center might affect the dynamics of stars and gas in those regions, subtly influencing the environment in which black holes grow and evolve. The relationship between dark matter and supermassive black holes is not yet well understood. But the fact that these two great mysteries of modern astrophysics, dark matter and black holes, may be connected in meaningful ways only deepens the sense that the universe is hiding something important from us, something that, once understood, will reshape our picture of how everything fits together. What is clear, looking across all of this, is that dark matter is not a passive background ingredient in the universe. It is an active architect. It built the scaffolding. It invited the galaxies in. It shaped their growth, their clustering, their environments. It left its fingerprints on the cosmic web that spans the entire observable universe. And it did all of this without ever emitting a single photon of light. The universe we can see, brilliant, intricate, breathtaking, is something like the decoration on a much larger and older structure. A structure we are still learning to read, one invisible thread at a time. There is a certain satisfaction in knowing that something exists, even when you cannot see it. The gravitational case for dark matter is so thorough, so consistent across so many different kinds of observation, that its existence is about as well established as anything in modern cosmology. The scaffolding is real. The cosmic web is real. The halos around galaxies are real. but knowing that something exists and knowing what it is are two entirely different things. Dark matter's role as the universe's great architect is well documented at this point. The clustering of dark matter, gas, and galaxies in the same cosmic regions, those vast filaments and dense nodes mapped across hundreds of millions of light-years, is exactly what you would expect if dark matter provided the initial gravitational framework and everything else gathered around it. The theory and the observations align with remarkable consistency. And yet, buried within that story, there is a detail that often gets overlooked. One that reaches further than galaxies, further than cosmic structure, and arrives, quietly, at something deeply personal. Dark matter may have played a role in the creation of the elements that make life possible. In the early universe, the only elements that existed in significant quantities were hydrogen, helium, and tiny traces of lithium, the lightest elements, forged in the first few minutes after the Big Bang. Everything heavier than that, every carbon atom in every living thing, every oxygen atom in every breath, every iron atom in every drop of blood, had to be made later. Made inside stars, through the slow nuclear burning of stellar cores, and then scattered across space when those stars died. But for that process to begin, stars had to form. And stars formed earlier, and in greater numbers, because dark matter had already built the gravitational structures they needed. Some researchers have suggested that dark matter's early influence may have accelerated the timeline for star formation enough to push the creation of heavy elements, the ones genuinely necessary for chemistry, for planets, for life, earlier into cosmic history than would otherwise have been possible. It is a subtle chain of causation, and scientists are careful not to overstate it. But the possibility is there, woven into the calculations. The invisible scaffolding of the universe may have helped set the table for everything that came after, including, eventually, us. It is the kind of thought that rewards sitting with for a moment. And then, naturally, the question reasserts itself. The one that has been waiting patiently since the very beginning of this story. What is dark matter actually made of? This is where the certainty ends and the speculation begins, and where physics becomes, in a different way, just as beautiful. Because the hunt for dark matter's identity has generated some of the most creative, ambitious, and genuinely strange ideas in modern science. It has pushed physicists to the edges of what is currently known and compelled them to imagine entirely new frameworks for understanding matter, force, and the fundamental structure of reality. The most straightforward possibility is also the one that has attracted the most attention over the past several decades. Dark matter may be made of a new kind of particle, something that exists in nature but has not yet been discovered, something that fits into the laws of physics without violating them, but that has simply never shown up in any detector or accelerator because it interacts with ordinary matter only very weakly, if at all. This idea has genuine theoretical appeal. The standard model of particle physics, the extraordinarily successful framework that describes all known particles and forces, is widely believed to be incomplete. There are good theoretical reasons, independent of dark matter entirely, to expect that new particles exist beyond those already catalogued. Dark matter may simply be one of them, or several of them, patiently waiting to be found. Among the candidate particles, two have historically stood out above the rest. The first are WIMPs, weakly interacting massive particles. The name is almost too convenient, but the physics behind it is serious. WIMPs are hypothetical particles with masses roughly in the range of protons and heavier nuclei, and they interact with ordinary matter through the weak nuclear force, the same force responsible for certain types of radioactive decay. They would be heavy enough to have the right gravitational influence, and weak enough in their interactions to have escaped detection so far. What made WIMPs particularly compelling for a long time was a coincidence that physicists found genuinely striking. If you calculate how many WIMPs would have been produced in the hot early universe, and how many would have survived as the universe cooled, you arrive at a number that is remarkably close to the observed density of dark matter today. This was not forced or adjusted to fit. It emerged naturally from the mathematics. Physicists called it the WIMP miracle, and for many years it made WIMPs the leading candidate by a wide margin. Dedicated experiments were built to find them. Enormous detectors, filled with liquid xenon or germanium crystals, were placed deep underground to shield them from cosmic rays, waiting for the rare moment when a dark matter particle might collide with an atomic nucleus and leave a detectable signal. Accelerators search for WIMPs in high-energy collisions. Space telescopes looked for the gamma rays that might be produced if WIMPs annihilated each other in regions of high dark matter density. So far, nothing definitive has been found. The WIMP miracle has not yet translated into a detection, and the most sensitive experiments have steadily closed off the parameter space where WIMPs were expected to hide. WIMPs are not ruled out, but they are considerably less favored than they once were. The second major candidate is the axion. Axions are quite different from WIMPs, far lighter, almost inconceivably so, with masses potentially billions or trillions of times smaller than the electron. They were originally proposed not to explain dark matter at all, but to solve a separate theoretical problem in quantum chromodynamics, the theory of the strong nuclear force. The fact that they might also account for dark matter was something of a bonus, and a compelling one. Axions interact with ordinary matter even more weakly than WIMPs, which makes them extraordinarily difficult to detect. But they have a particular property that experimentalists have learned to exploit. In the presence of a strong magnetic field, axions can convert into photons, real, detectable light. Experiments have been designed specifically around this conversion, using powerful magnets and sensitive microwave detectors, carefully tuned to the frequency range where axion-produced photons might appear. The search is slow and painstaking. Axions, if they exist, would occupy a vast range of possible masses, and experiments can only probe narrow slices of that range at a time. But the technology has been improving steadily, and the search is gaining momentum. Beyond WIMPs and axions, however, theorists have been thinking much more broadly. And this is where the ideas become genuinely expansive. Some scientists have proposed that dark matter may not be a single particle at all, but part of what is called a dark sector, an entire hidden realm of particles and forces that exists alongside our own but interacts with it only through gravity, or through a small number of very faint connections. The idea of a dark sector is, in a sense, a natural extension of the kind of thinking that led to the Standard Model in the first place. Our own visible universe contains multiple kinds of particles and multiple forces: electromagnetism, the weak force, the strong force, interacting in complex ways. There's no compelling reason why the dark sector should be simpler. It might contain its own particles, its own forces, perhaps even its own chemistry, invisible to us not because it is fundamentally unknowable, but because the connection between our sector and theirs is extremely faint. Modern theoretical papers have explored dark sectors with multiple particles, models where dark matter is not one thing but a family of things, interacting with each other through dark forces, forming structures we cannot see, governed by physics we have not yet written down. Some of these models predict that dark matter particles might interact with each other in ways that leave subtle signatures on the distribution of dark matter in galaxies, signatures that, with careful enough observation, might someday be detected. The connections between the dark sector and the visible sector, where they exist, are often thought to run through specific particles in the Standard Model. Two that come up frequently in theoretical work are the Higgs boson and the Z boson, particles that have already been discovered and studied at colliders like the Large Hadron Collider at CERN. If dark matter interacts with ordinary matter through these particles, even very weakly, then collider experiments might catch a glimpse of it, perhaps by observing collisions where energy or momentum appears to go missing, carried away by dark matter particles that leave no other trace. This is an active area of theoretical and experimental work. Physicists build models, derive predictions, and then check those predictions against the data from colliders and detectors. So far, no confirmed signal. But the models are rich, the predictions varied, and the experiments are continuously improving. Then there are the ideas at the very frontier of current thinking, the ones still forming, still being tested against observation and theory. Some researchers working in 2026 have been exploring a striking possibility, that dark matter does not come in just one form, but in two distinct types, with different properties and perhaps different origins. This two-component picture of dark matter is not merely a theoretical curiosity. It was proposed, at least in part, to explain something specific and puzzling: an excess of gamma rays detected coming from the center of the Milky Way. The galactic center is an extraordinary and complicated place. It contains a supermassive black hole, dense star clusters, enormous clouds of gas and magnetic field structures unlike anything in the quieter outer reaches of the galaxy. It is also, according to dark matter models, a region of very high dark matter density, and high density means a higher probability of dark matter particles annihilating each other, which in certain models would produce gamma rays. Astronomers have indeed observed an excess of gamma rays from the galactic center, beyond what can be easily explained by known astrophysical sources. For years, the dark matter annihilation explanation has been one of the leading candidates, alongside the possibility that the excess comes from an unresolved population of rapidly spinning neutron stars called millisecond pulsars. The two-component dark matter proposal enters here as an attempt to fit the gamma ray signal more precisely. Different types of dark matter, with different masses and interaction rates, would annihilate at different rates and produce gamma rays at different energies. By invoking two components rather than one, theorists can potentially match the observed signal more accurately than single-component models allow. Whether this idea is correct remains to be seen. It is the kind of proposal that sits at the edge of what current data can confirm or refute, compelling enough to take seriously, uncertain enough to hold with appropriate humility. Science at the frontier often looks exactly like this: multiple competing ideas, each with some supporting evidence and some unresolved tensions, waiting for the observation or experiment that will finally separate them. What is striking, looking across all of these proposals, WIMPs, axions, dark sectors, two-component models, Higgs portal interactions, is the sheer breadth of the theoretical landscape. Dark matter might be one particle or many. It might interact with ordinary matter rarely or almost never. It might have its own rich internal structure, or it might be the simplest possible thing. We genuinely do not know yet which of these directions, if any, points toward the truth. What we do know is that the answer, when it comes, will be one of the most significant discoveries in the history of science. It will not merely identify a new particle. It will open a window into a sector of reality that has been invisible to us for the entire history of human inquiry. It will change our understanding of what matter is, what forces exist, and perhaps what the universe is, at its deepest level, made of. The invisible architect of the cosmos is waiting to introduce itself. We are still learning how to ask the right questions. The gamma-ray excess at the center of the Milky Way remains one of those puzzles that refuses to resolve itself cleanly. The two-component dark matter idea, the proposal that dark matter might come in two distinct varieties rather than one, was designed, in part, to match the shape and energy distribution of that signal more precisely than simpler models could manage. But there is a natural test for any idea like this. If the gamma-ray signal really does come from dark matter annihilation, and if the properties of the dark matter responsible can be pinned down, then you should be able to make predictions about what you would see in other environments where dark matter is present. Dwarf galaxies, those small and nearly pure dark matter systems discussed earlier, provide exactly that kind of test. They contain dark matter in abundance, but their environments are far simpler than the chaotic, dense center of the Milky Way. If the galactic center signal is genuinely dark matter in origin, and if the same dark matter exists in dwarf galaxies, you would expect to see some signal from those systems as well, perhaps weaker, given their lower overall density, but present. So far, the gamma-ray signals from dwarf galaxies have been frustratingly quiet. Weaker than some dark matter models would predict, or simply absent at the sensitivity levels current telescopes can reach. The two-component model has been explored as one way to reconcile this. If dark matter comes in two forms, perhaps the mix of those forms, or the way they interact and annihilate, differs subtly between the dense galactic center and the more diffuse environments of dwarf galaxies, producing a stronger signal in one place and a weaker one in the other. Whether this explanation holds up under continued scrutiny is still an open question. But it illustrates something important about how science at this frontier operates. Every new observation becomes both a potential confirmation and a potential constraint. Every piece of data narrows the space of what dark matter can be, even when it does not yet tell us what dark matter is. There is, in fact, a growing conversation among researchers about language itself, about whether the term we have been using all along is entirely accurate. Dark matter. It is a name that has served well for nearly a century, capturing the essential strangeness of something that contributes mass and gravity without contributing light. But some researchers have begun suggesting that invisible matter might actually describe it more precisely. Not dark, in the sense of absorbing light or being somehow dim or shadowy. Simply invisible, transparent to light, untouched by electromagnetism, present everywhere and detectable by almost nothing. The distinction is subtle but meaningful. Darkness implies an absence, a shadow, something that blocks or absorbs. Invisibility implies something different, a complete independence from the mechanisms by which we ordinarily perceive things. Dark matter does not block light. It does not absorb it. It simply has no relationship with light at all. It exists entirely outside the electromagnetic story of the universe. Whether the name changes in common usage remains to be seen. Science has a way of preserving its historical terminology long after more accurate alternatives have been proposed. But the impulse behind the suggestion is worth noting. As our understanding deepens, the words we use to describe things matter. They shape intuition, guide thinking, and sometimes either illuminate or obscure the true nature of what we are studying. For now, dark matter remains dark matter. But the conversation around it is anything but static. And nowhere is that more evident than in the extraordinary lengths to which scientists have gone to find it. The search for dark matter is one of the most ambitious experimental programs in the history of physics. It spans continents, reaches into the deepest accessible points underground, pushes the boundaries of engineering and material science, and demands a level of sensitivity that would have seemed almost fantastical just a few decades ago. The fundamental challenge is this. If dark matter particles exist and occasionally interact with ordinary matter, even very rarely, through the weak force or some similarly faint mechanism, then every now and then, one of them should collide with an atomic nucleus in a detector. The collision would be gentle, depositing only a tiny amount of energy. But it would be real and, in principle, detectable. The problem is background noise. The world is full of particles and radiation that can mimic the signal of a dark matter interaction. Cosmic rays rain down from space constantly. Natural radioactivity in rocks and building materials produces a steady background of particles. Even the atoms in the detector itself can occasionally produce false signals through ordinary quantum mechanical processes. Against this relentless background, the hypothetical dark matter signal would be extraordinarily rare, perhaps a handful of events per year, or fewer, in a detector containing hundreds of kilograms of material. The solution, developed and refined over decades of careful work, is to go deep underground. Rock is an excellent shield. A kilometer of solid rock above a detector absorbs the vast majority of cosmic ray particles that would otherwise contaminate measurements. The deeper you go, the quieter the environment becomes, not completely quiet, because neutrinos pass through any amount of rock with ease, and natural radioactivity from the surrounding geology must still be carefully managed, but far quieter than the surface. Underground laboratories around the world, beneath mountains, beneath the ocean floor, beneath the flat plains of northern Canada, have been built specifically to provide this shielded environment for dark matter detectors and other sensitive physics experiments. Canada's Snow Lab, located nearly 2 kilometers underground in an active nickel mine in Sudbury, Ontario, is one of the deepest and cleanest such facilities on Earth. And it is home to some of the most sophisticated dark matter searches currently operating anywhere in the world. Among the experiments running there is one that has pushed the boundaries of what is physically achievable in terms of temperature. To isolate faint signals from potential dark matter interactions, certain detectors need to be cooled to temperatures just barely above absolute zero, the theoretical minimum temperature where all thermal motion of atoms ceases entirely. Absolute zero sits at approximately -273 degrees Celsius. Some dark matter detectors at Snow Lab and similar facilities operate at temperatures only a few thousandths of a degree above that limit, in a thermal regime that is actually colder than the average temperature of deep space. At those temperatures, the thermal noise that would otherwise swamp any faint signal is reduced to nearly nothing. The detector material, germanium or silicon crystals, in some cases, becomes extraordinarily sensitive. Even the tiny vibration produced when a particle strikes a nucleus can be measured, because in that near absolute zero environment, even very small energy deposits produce measurable changes. Maintaining this environment is itself a feat of engineering. The cryogenic systems required are complex, carefully calibrated, and deeply impressive. The detectors must be isolated from vibration, from electromagnetic interference, from any stray heat source. Building and operating them requires expertise drawn from physics, materials science, mechanical engineering, and electrical engineering simultaneously, a genuine collaboration across disciplines. One of the major experiments at the forefront of low-mass dark matter searches is SuperCDMS, the Supercryogenic Dark Matter Search. SuperCDMS is specifically designed to look for dark matter particles at the lower end of the mass range, lighter particles than the WIMPs that earlier experiments primarily targeted. The reason this matters is that detection sensitivity is closely tied to the mass of the particle you are looking for. Heavier particles transfer more energy to the nuclei they strike, making their collisions easier to detect. Lighter particles transfer less energy, and at some point, the energy deposited falls below the detection threshold of conventional detectors. SuperCDMS addresses this by using detectors of exquisite sensitivity, operated at those extraordinary ultra-cold temperatures, capable of measuring energy deposits far smaller than earlier experiments could resolve. This opens a new window into the dark matter landscape, a region of lower masses that remains largely unexplored, and where a genuine discovery could still be waiting. The experiment has been in development and deployment at Snow Lab, and its scientific reach extends into territory where few searches have gone before. But there is a complication on the horizon. A fundamental one. And it goes by a quietly evocative name: the neutrino fog. Neutrinos are ghostly particles produced in enormous quantities by the Sun, by supernovae, by the interactions of cosmic rays in the atmosphere. Like dark matter, they interact with ordinary matter only very weakly. Unlike dark matter, we know exactly what they are and where they come from. And they are everywhere, trillions of solar neutrinos pass through every square centimeter of the Earth every second. For most of the history of dark matter detection, neutrinos were not a serious concern. The energies and interaction rates involved in neutrino collisions were distinct enough from those expected for dark matter that they could be distinguished or ignored. But as detectors have become more and more sensitive, as the technology has improved to the point where genuinely rare events can be recorded, neutrinos are becoming a problem. At a certain level of sensitivity, solar neutrinos begin to interact with detector nuclei at a rate comparable to the expected rate of dark matter interactions. They become, in a technical sense, an irreducible background, a fog of real physical events that mimics the signature of dark matter and cannot be shielded against the way cosmic rays can. No amount of rock will stop a neutrino. This neutrino fog represents something of a conceptual wall for direct detection experiments. It does not make dark matter detection impossible, but it makes it significantly harder. To push through the fog, experiments will need to not just detect events but characterize them in enough detail to distinguish neutrino interactions from dark matter interactions, which requires even more sophisticated detectors, more precise energy measurements, and potentially directional sensitivity, the ability to determine which direction a particle came from and compare it against the known direction of the Sun. It is a real challenge, and the experimental community is actively working on strategies to meet it. But it also marks a natural transition point in the history of dark matter searches, a moment where the easy discoveries, if any were ever going to be easy, have given way to something more demanding. While direct detection experiments dig deeper underground and cool their detectors ever closer to absolute zero, the search also continues at particle colliders, most prominently at CERN's Large Hadron Collider near Geneva. The collider approach is conceptually different from direct detection. Rather than waiting for dark matter particles to arrive and interact in a passive detector, collider experiments try to create them, smashing protons together at energies high enough that new, exotic particles might be produced in the collision debris. If dark matter particles are produced in a collision, they would escape the detector without leaving any signal, but their departure would be visible as missing energy, a measurable imbalance in the total momentum of everything else produced in the event. The Large Hadron Collider has conducted extensive searches of this kind, looking for events where energy goes missing in ways that cannot be accounted for by known particles. So far, no confirmed dark matter signal has emerged from these searches. But the collider approach remains valuable, because it can probe types of dark matter that direct detection experiments are less sensitive to, and because understanding the energy scales at which new particles might appear requires exactly the kind of high-energy exploration that colliders provide. Together, direct detection underground and high-energy searches at colliders form a complementary picture, approaching the same mystery from different directions, each probing regions of the theoretical landscape that the other cannot easily reach. And the byproducts of this search have not been confined to physics. One of the quieter stories in the history of dark matter research is how much useful technology it has generated along the way. The extreme demands of dark matter experiments, the need for ultra-sensitive detectors, cryogenic systems operating near absolute zero, low-noise electronics, highly purified materials, and sophisticated data analysis, have driven advances in fields that extend well beyond particle physics. Cryogenic technology developed for dark matter detectors has found applications in medical imaging and quantum computing. Sensor technologies refined in the search for rare particle interactions have influenced materials science and precision measurement more broadly. Superconducting devices, developed partly in the context of low-temperature physics experiments, underpin technologies ranging from MRI machines to some of the most advanced computing architectures currently being explored. The computing and data analysis methods developed to sift through enormous datasets looking for rare signals have contributed to machine learning and statistical analysis techniques used across many fields of science and industry. This is a pattern that repeats throughout the history of fundamental physics research. The search for answers to the deepest questions about the universe consistently generates tools, techniques, and knowledge that find practical applications no one anticipated at the outset. Dark matter research is no exception. The hunt for something invisible, carried out in the coldest and quietest places humans have ever built, has left a trail of useful innovations across multiple fields. The detectors keep running. The data keeps accumulating. The theorists keep refining their models. And the neutrino fog waits at the edge of what is currently achievable, a natural boundary beyond which the next generation of experiments will need to venture. Somewhere, in all of this, in the cold silence of underground laboratories, in the controlled violence of particle collisions, in the careful mathematics of theoretical models, the answer may already be within reach. Or it may require tools and ideas that have not yet been invented. Either way, the search continues. Patient, methodical, and driven by one of the oldest impulses in human nature, the need to understand what the world is actually made of, even when that world refuses to show itself easily. For most of its history, the search for dark matter has been framed primarily as a hunt. A search for the particle, the fundamental unit of whatever dark matter actually is, that could be isolated, identified, and held up as the answer to one of science's greatest mysteries. The experiments built for this purpose have been extraordinary achievements of human ingenuity, and the hunt is far from over. But something is shifting in the field. Quietly, almost imperceptibly at first, and now with growing momentum. Some of the most significant recent work in dark matter research is not focused on detecting a particle at all. It is focused on something grander in scale and different in character, the project of mapping the invisible universe itself. Not just confirming that dark matter is there, but measuring where it is, how it is distributed, how dense it becomes in different environments, and how its structure across cosmic scales compares with the predictions of theoretical models. This shift, described in some 2026 reports as a transition from hunting particles to surveying the invisible universe, represents a maturation of the field. It acknowledges that even without knowing what dark matter is made of, there is an enormous amount to be learned from studying how it behaves at the largest scales. And it has been made possible by a generation of telescopes and observational tools of unprecedented power, none more transformative, at this particular moment, than the James Webb Space Telescope. But to understand what these new maps represent, it helps to step back and appreciate the technique that makes them possible. Gravitational lensing, the bending of light by mass, has been a tool for studying dark matter for decades. In its most dramatic form, strong lensing, a massive foreground object bends the light from a distant background source so severely that it produces visible arcs, rings, or multiple images. These dramatic distortions are beautiful and informative, but they require a fortunate alignment of foreground and background objects, and they probe only the densest concentrations of mass. Most of the universe, however, is not composed of dramatic concentrations. Dark matter is spread across vast volumes of space, distributed in filaments and halos and diffuse sheets that produce only very subtle distortions in the light passing through them. Detecting this requires a technique called weak gravitational lensing, and it is a technique of considerable elegance. When light from distant galaxies passes through regions of space containing dark matter, the shapes of those galaxies are very slightly distorted. Not enough to create the dramatic arcs of strong lensing, but enough to produce a tiny, coherent stretching of galaxy images, a tendency for galaxies to appear slightly more elongated in directions aligned with the dark matter structure they have passed through. The effect on any individual galaxy is tiny, far smaller than the natural variation in galaxy shapes, and completely undetectable on its own. But galaxies are not rare. The universe contains hundreds of billions of them, and modern telescopes can observe millions or hundreds of millions in a single survey. When you look at the shapes of vast numbers of galaxies statistically, the tiny coherent signal of weak lensing emerges from the noise. By analyzing the correlations in galaxy shapes across the sky, astronomers can reconstruct the distribution of mass, including the invisible dark matter, along the line of sight. It is, in a sense, reading the fingerprints that dark matter leaves on the light of the entire universe. Not the dramatic fingerprints of direct interaction, but the subtle, statistical fingerprints of space-time geometry. The Cosmos Webb survey is one of the most ambitious applications of this technique ever undertaken, and its dark matter map represents a genuine landmark in observational cosmology. Cosmos Webb was conducted using the James Webb Space Telescope, and it focused on a region of sky known as the Sexton's Field, a patch of the sky that previous surveys had already studied with other telescopes, providing a rich context of existing data. What Webb brought to this region was a combination of imaging depth, resolution, and infrared sensitivity that no previous instrument could match. The resulting dark matter map was built from weak gravitational lensing measurements across a field containing roughly 800,000 galaxies. 800,000 individual galaxies, each one a faint smear of light whose subtle shape distortion carries information about the dark matter lying between it and us. Analyzing the shapes of that many galaxies, correcting for the intrinsic variations in galaxy morphology, accounting for the telescope's own optical properties and the effects of the atmosphere, the technical challenges involved in turning raw images into a dark matter map are formidable. The fact that it can be done at all is a testament to decades of methodological development. What emerged from this analysis was described, with some justification, as the first page of a new atlas of the invisible universe. Not the complete atlas, that will take many more observations, many more surveys, likely many more years. But the first page, a demonstration that the project is underway, that the tools are ready, and that the universe is beginning, slowly and on its own terms, to reveal the shape of its hidden architecture. The map shows dark matter distributed across the Sextans field in the way theoretical models broadly predict, concentrated along filaments, denser at the nodes where filaments intersect, thinner and more diffuse in the voids between. The large-scale structure visible in the map echoes the cosmic web picture built up over decades of observation and simulation. But it does so with a clarity and detail that previous maps could not achieve, because the depth and resolution of Webb's imaging allows fainter and more distant galaxies to be included in the analysis, extending the reach of the map and sharpening its features. The map released in 2026 based on Webb observations was described in multiple contexts as the largest dark matter map ever produced with the James Webb Space Telescope, and simultaneously as the most detailed. Those two distinctions together are significant. Larger maps trade detail for coverage. More detailed maps often sacrifice extent. Achieving both simultaneously requires both extraordinary observational data and sophisticated analysis techniques, and the Cosmos Webb result represents a meaningful advance on both fronts. What does it actually look like, this map of the invisible? There is something almost meditative about visualizing it. The map does not show stars or galaxies directly, it shows mass. Regions of higher dark matter density appear brighter in the false color representations scientists use to make the data visible, and regions of lower density appear darker. Filamentary structures stretch across the field, connecting bright concentrations in a web-like pattern. Between them, the voids are quiet, not empty, but sparse, their dark matter content thin and diffuse. Superimposed on this invisible architecture, the visible galaxies trace the same structures. Where dark matter concentrates, galaxies cluster. Along the filaments, galaxies are more numerous. In the voids, they are rare. The correlation is not perfect. The relationship between dark matter distribution and galaxy distribution is complex and shaped by many physical processes, but it is real and consistent, one more confirmation of the picture that has been assembling for decades. What makes the new generation of Webb-based maps particularly exciting is the precision with which dark matter's density and three-dimensional structure can now be measured. Earlier maps were valuable but coarse. They could identify where dark matter was concentrated in a broad sense, but could not measure those concentrations precisely enough to make detailed comparisons with theoretical predictions. The sharpness of Webb's imaging, combined with the sheer number of galaxies available for lensing analysis, allows the new maps to approach dark matter's distribution with a level of quantitative precision that was previously out of reach. This matters enormously for testing theories. The standard model of cosmology, the Lambda CDM model, which combines dark energy and cold dark matter, makes specific predictions about how dark matter should be distributed at different scales. It predicts the sizes of dark matter halos, the density profiles within them, the prevalence and structure of cosmic filaments. As dark matter maps become more precise, they provide increasingly stringent tests of these predictions. Agreements confirm and refine the model. Discrepancies, if they emerge at sufficient statistical significance, could point towards something new, a modification of the dark matter model, a different kind of dark matter, or something in the cosmological framework that needs revisiting. The field is, in this sense, entering a new phase of its maturity. The qualitative picture: dark matter exists, it forms halos around galaxies, it shapes the cosmic web, has been established for long enough that it is no longer seriously questioned. What is now being pursued is the quantitative picture. How much dark matter is there in a given region? How precisely does its density profile match theoretical predictions? How does its distribution at different cosmic epochs compare, and what does that comparison tell us about how dark matter behaves over cosmic time? These are harder questions than the qualitative ones, but they are also more discriminating. They have the potential to distinguish between dark matter models that the qualitative evidence cannot separate. A universe filled with WIMPs and a universe filled with axions might look broadly similar in terms of the large-scale structure they produce, but they could differ subtly in the details, the density profiles of halos at small scales, the prevalence of the smallest dark matter structures, the fine texture of the cosmic web. Precise mapping is one of the tools that could, in principle, reveal these differences. Large sky surveys operating alongside Webb are also contributing to this project. Programs designed to image hundreds of millions of galaxies across vast areas of sky, applying weak lensing analysis at cosmological scales, are producing maps that complement Webb's deeper, higher-resolution views of smaller fields. Where Webb sees fine detail in a relatively narrow cone of the universe, these wide-field surveys capture the broad sweep of cosmic structure across much larger angles. Together, they cover both the small-scale details and the large-scale context that a complete picture of dark matter's distribution requires. There is something deeply satisfying about the way this effort is unfolding. For most of human history, maps have been records of the known world, coastlines charted by sailors, territories surveyed by explorers, star positions catalogued by astronomers. The idea of mapping something that cannot be seen, something that leaves no direct imprint on any instrument, using only the subtle statistical distortions it imprints on the light of hundreds of thousands of galaxies, this would have seemed, not long ago, like an impossible ambition. And yet here we are. The first pages of the atlas are written. The invisible universe is taking shape on paper, rendered in the language of mathematics and the technology of the most powerful space telescope ever built. Each new observation adds resolution, adds extent, adds depth. Each new map narrows the constraints on what dark matter can be and how it must behave. The atlas of the invisible universe is incomplete, and will remain so for a long time. But the project of assembling it has begun in earnest, and the maps already in hand are extraordinary things, records of a universe that existed for billions of years before anyone had the means to even ask what it was made of, let alone begin to draw its outline. The outline is emerging now. Slowly, patiently, one galaxy at a time. Numbers, and science, can sometimes do something that words alone cannot. They can reach past the abstract and land somewhere genuinely felt, a sudden, quiet sense of scale that reshapes how you understand something. The latest dark matter maps produced using the James Webb Space Telescope are full of numbers like that. Consider the resolution first. The most recent web-based weak lensing maps are roughly twice as sharp as any comparable map produced before them. Not a marginal improvement, not a refinement at the edges of measurement, twice as sharp. The features visible in these maps, the fine structure of filaments, the density gradients within halos, the places where dark matter concentrates and where it thins, all of it rendered with a clarity that earlier instruments simply could not provide. The difference is the difference between a sketch and a detailed drawing. Both tell you something, but one tells you considerably more. Then there is the number of galaxies. Earlier ground-based weak lensing maps of comparable regions were built from tens of thousands of galaxy-shape measurements. The new Webb maps are built from approximately 250,000 galaxies. That is not just a larger sample in the statistical sense, though it is certainly that. It represents a fundamentally different depth of observation. Webb's seeing galaxies that are fainter, more distant, and more numerous than ground-based telescopes can resolve, each one adding its tiny contribution to the overall lensing signal, and the cumulative effect of all those contributions being a map of dramatically greater precision and reliability. 250,000 galaxies, each one a faint smear of ancient light, each one carrying in the subtle distortion of its shape a message about the dark matter that lies between it and us. The patience required to collect that data, and the ingenuity required to decode it, is something worth pausing to appreciate. The area of sky covered by this map is another number that rewards attention. It spans a region roughly 2.5 to 3 times the apparent size of the full moon as seen from Earth. That might sound modest, a small patch of sky, a narrow window on the universe. But remember what is contained within it. At the distances involved, a region that appears 3 moon widths across encompasses an almost incomprehensible volume of space. The light from the most distant galaxies contributing to this map has been traveling for 8 to 10 billion years before reaching Webb's mirrors. 8 to 10 billion years. The universe itself is approximately 13.8 billion years old. The light captured in these observations left its source when the universe was less than half its current age, when galaxies were younger and closer together, when the large-scale structure of the cosmos was still actively assembling itself into the web-like pattern we see today. What this means, practically, is that the map is not just a snapshot of where dark matter is now. It is a record of where dark matter was, and how it was distributed across a substantial portion of cosmic history. It is a map with depth, in the literal sense. The galaxies at different distances show you dark matter at different epochs, and by comparing those different layers, scientists can watch the dark matter distribution evolve across billions of years. This is something genuinely new. Previous dark matter maps, limited to shallower depths and smaller samples, could provide snapshots of relatively recent cosmic structure. The new Webb maps reach back far enough to show how that structure developed, how the dark matter filaments and halos that exist today were already being laid down when the universe was in its relative youth. And there, in that deep historical record, something important shows up. The visible matter in the region mapped, the ordinary baryonic matter that makes up all the stars, gas, dust, and galaxies, constitutes only about 4% of the universe's total matter content in that field. 4%. The rest is dark matter, as expected, and the map's sensitivity to the dark matter component reflects that overwhelming dominance. But what makes this particular observation so meaningful is not just the percentages. It is what the map reveals about the relationship between that 4% of visible matter and the 96% that is dark. They overlap. Through cosmic history, across 8 to 10 billion years of observations captured in a single map, the dark matter and the ordinary matter trace the same structures. Where dark matter concentrates into clusters, visible matter clusters too. Where dark matter forms filaments, galaxies align along them. Where dark matter leaves voids, ordinary matter is sparse. The two components of the universe, so different in their fundamental nature, have been moving together, evolving together, building the same structures together, across the entire span of cosmic history captured in these observations. The map showed clusters, filaments, and galaxy groups, the full hierarchy of cosmic structure, from the grandest scales down to the individual clumps where galaxies gather, and in each of these features, dark matter and ordinary matter were found together. Not just in the same general regions, but tracing each other with a fidelity that speaks to how deeply intertwined their histories are. This coevolution is, in one sense, exactly what the theoretical models predicted. Cold dark matter models, the ones that have underpinned cosmological thinking for decades, expect dark matter and ordinary matter to cluster together, because ordinary matter flows toward dark matter's gravitational wells and builds its structures there. The prediction is that you should see them together, at all scales and across all cosmic time. But prediction and confirmation are different things. Seeing it directly, in a map that reaches back 10 billion years and resolves the structure of the cosmic web at this level of detail, is not the same as deriving it from equations. It is the universe confirming, in its own language, that the theoretical framework has been capturing something real. It also adds nuance to the picture in ways that are scientifically productive. The degree to which dark matter and ordinary matter overlap, and the ways in which they do not perfectly overlap, carries information. Ordinary matter is subject to processes that dark matter is not. It can cool, condense, form stars, be heated by those stars, be blown apart by supernovae, be redistributed by the enormous energy output of active galactic nuclei. These processes can push ordinary matter around within its dark matter halo, creating subtle offsets between the distribution of visible matter and the distribution of dark matter, even in regions where both are present. By comparing the dark matter maps with the distribution of visible galaxies and gas in the same regions, scientists can begin to quantify these offsets and use them to understand the physical processes that shaped both components. It is, in this sense, a two-way analysis. The dark matter map illuminates the structure that visible matter inhabits. And the distribution of visible matter, compared against the dark matter map, illuminates the astrophysical processes that have moved things around within that structure. The suggestion from the newest maps, that dark matter and ordinary matter evolved together across cosmic history, carries a particular significance when viewed against the background of some earlier tensions in the field. There have been periods in recent years when measurements of the large-scale distribution of matter in the universe appeared to show subtle discrepancies with the predictions of the standard cosmological model. Different surveys, using different techniques, produced slightly different values for parameters describing how clumped or smooth the matter distribution is. These tensions, not large enough to definitively overthrow the standard model, but persistent enough to take seriously, raised the question of whether the model was missing something, whether dark matter behaved slightly differently than assumed, or whether the measurements themselves harbored unresolved systematic errors. The new web-based maps are contributing to this ongoing conversation. With their greater depth, sharper resolution, and larger galaxy samples, they provide measurements of the matter distribution that are more precise than previous lensing studies. Whether they will ultimately resolve the tensions, confirm them, or complicate the picture further is still being worked out as the data is analyzed and compared with other surveys. But they represent exactly the kind of improved observational precision that the field needs to make progress on these questions. There is a quality to this work, the mapping of the invisible, the tracing of cosmic history through the shapes of distant galaxies, the assembling of an atlas that reaches 10 billion years into the past, that feels, in a certain light, like one of the great intellectual projects of our era. Not because it generates applications or technologies, though it does. Not because it resolves an immediate practical problem, because it does not. But because it addresses, as directly as science can, one of the most fundamental questions it is possible to ask. What is the universe made of? The answer, it turns out, is mostly something we cannot see. Something that has been there since long before the first stars formed, that shaped the framework within which every galaxy grew, that has traveled alongside ordinary matter across 10 billion years of cosmic evolution, leaving its fingerprints on the shapes of distant galaxies for Webb's mirrors to record. Each new map is a layer added to the atlas. Each galaxy whose shape has been measured is a data point in a picture that is slowly, painstakingly coming into focus. The resolution is improving. The depth is increasing. The coverage is expanding. And somewhere in all of that data, in the filaments and clusters and galaxy groups traced across billions of light years and billions of years, the full story of dark matter and the universe it helped to build is waiting to be read. We are learning the language. Page by page, map by map, galaxy by galaxy. The maps were already remarkable before the finer details emerged. At the broad scale, the filaments stretching across hundreds of millions of light years, the dense nodes where galaxy clusters gather, the vast quiet voids between, the new web-based dark matter maps confirmed what decades of theory and observation had predicted. The cosmic web was there, rendered in greater detail and across greater depth than any previous map had achieved. That alone would have made the work significant. But when scientists examine the maps more closely, at smaller scales and with greater attention to the subtler features, something additional appeared. Clumps of dark matter that had not been seen before. Concentrations of mass at scales smaller than previous surveys could resolve, showing up in the web data with enough clarity to be identified and studied. Fine structures within the broader web, not just the major filaments and clusters, but the more intricate texture of dark matter distribution at intermediate scales, the places where the cosmic web frays into smaller tendrils and knots. This is one of the areas where the improvement in resolution makes a genuine scientific difference. A map that is twice as sharp does not just show you the same features more clearly. It shows you features that were invisible before, structures that exist at scales below the resolution threshold of earlier instruments. The discovery of previously unseen dark matter clumps in the Webb maps is not a surprise in the sense that theory predicted nothing would be there. It is a confirmation that structure exists at these scales, and an opening of a new observational window onto dark matter's behavior at finer and finer levels of detail. These smaller structures matter for testing theories. The distribution of dark matter at small scales, how many small clumps there are, how dense they are, how they are distributed relative to larger halos, is sensitive to the fundamental properties of dark matter in ways that large-scale structure is not. Different dark matter models predict different small-scale behaviors, and observations at these scales can, in principle, discriminate between them. The maps are, in this sense, not just beautiful records of cosmic structure. They are precision instruments for probing the nature of dark matter itself. In the nature of dark matter, it is becoming increasingly clear, may be more complex than the simplest models assumed. In 2026, a report based on Hubble Space Telescope observations described a galaxy that appears to consist almost entirely of dark matter, potentially up to 99% of its total mass. This is not the first galaxy to be identified as unusually dark matter-rich. In recent years, a class of objects called ultra-diffuse galaxies has attracted considerable scientific attention, precisely because some of them appear to have far higher ratios of dark matter to ordinary matter than typical galaxies. But a galaxy that is 99% dark matter, if confirmed, would sit at the extreme end of that distribution, among the most dark matter-dominated objects ever identified. What makes a galaxy end up with almost no ordinary matter? The mechanisms proposed are varied. Tidal stripping, the gravitational pulling away of gas and stars by a larger neighboring galaxy, can remove ordinary matter while leaving the dark matter halo largely intact. Some ultra-diffuse galaxies appear to have formed in environments where the conditions for efficient star formation were never established, leaving behind a dark matter structure with only the barest trace of visible material. Others may have had their gas content blown out by early bursts of star formation or by the energy of active galactic nuclei. Whatever the mechanism in this particular case, a galaxy that is 99% dark matter is an extraordinary laboratory. The behavior of the system, its dynamics, its structure, its interaction with neighbors, is determined almost entirely by dark matter. Studying it in detail offers a nearly uncontaminated view of dark matter's properties, with ordinary matter contributing almost nothing to confuse the picture. Confirmation of the result requires further observation and analysis, as is standard for any claim at the edge of what current data can support. But the finding, even in its preliminary form, adds to a growing body of evidence suggesting that the range of environments in which dark matter exists, and the range of ratios in which it mixes with ordinary matter, is broader and more varied than earlier surveys had fully revealed. Meanwhile, at a more fundamental level, some of the most intriguing recent developments concern not where dark matter is, but how it behaves. The simplest version of cold dark matter, the model that has been the backbone of cosmological thinking for decades, treats dark matter particles as essentially non-interacting with each other. They respond to gravity, they form halos, they cluster and flow, but they do not interact significantly with other dark matter particles through any force other than gravity. This is the cold, collisionless picture. Simple, mathematically tractable, and broadly consistent with observations at large scales. But some recent research has begun to suggest that this picture may be incomplete. That dark matter may, in fact, interact with itself through forces beyond gravity. That dark matter particles may scatter off each other, influence each other's trajectories, and redistribute themselves within halos in ways that the simple collisionless model does not capture. This idea, self-interacting dark matter, has been explored theoretically for some years, but recent analyses have given it new observational relevance. The argument for considering it comes partly from a set of persistent, nagging discrepancies between the predictions of the simplest cold dark matter models and what is actually observed, particularly at small scales. One of these discrepancies concerns the density profiles of dark matter halos. The simplest models predict that dark matter halos should be densest at their very centers, with the density rising steeply as you move toward the core, a profile sometimes described as cuspy. But observations of certain galaxies, particularly dwarf galaxies and low-surface brightness galaxies, suggest that the dark matter density at their centers may be more uniform, a flatter core rather than a steep cusp. This cusp-core tension, as it is known, has been discussed for decades, and various explanations have been proposed, including the redistribution of dark matter by the energy of supernovae and stellar feedback. Self-interacting dark matter offers another possible explanation. If dark matter particles scatter off each other, energy can be transferred from the dense, high-velocity inner regions of a halo to the sparser outer regions, a process analogous to thermal conduction, smoothing out the steep central density peak and producing a flatter core. The degree of smoothing depends on the interaction rate, which in turn depends on the cross-section for dark matter self-interaction, a parameter that theorists can vary and compare against observations. Some recent analyses have found that models incorporating a modest level of self-interaction fit the observed density profiles of certain systems better than the purely collisionless model. The effect is not enormous, and it is not definitively confirmed, but it is consistent enough across a range of observations to take seriously. There is also growing interest in whether dark matter's behavior differs across different cosmic scales, whether properties that work well for describing dark matter in galaxy clusters also work well for describing it in dwarf galaxies, or whether the behavior changes in ways that a more complex model would need to accommodate. This scale dependence question is exactly the kind of thing that the new generation of precise observations is positioned to test. In galaxy cluster studies, the standard cold dark matter model performs impressively in some tests. The overall distribution of dark matter in large clusters, the way clusters cluster with each other, the statistics of their masses, these things match theoretical predictions reasonably well. But in other tests, particularly those probing the inner structure of clusters or the behavior of dark matter in the regions where two clusters have interacted, the picture is less clean. Some studies find density profiles that deviate from predictions. Others find that the dark matter distributions in merging clusters, while broadly consistent with the expected behavior, have features that a self-interacting model fits somewhat better. None of these tensions, taken individually, is sufficient to overturn the standard model. And there are always questions about whether the discrepancies reflect genuine departures from simple cold dark matter, or whether they reflect the complex effects of ordinary matter, stellar feedback, supernovae, active galactic nuclei, redistributing mass within halos in ways that simulations do not fully capture. Disentangling these two possibilities is one of the central challenges in the field right now. One of the most promising arenas for resolving these questions is the study of small dark matter subhalos. In the hierarchical picture of structure formation that cold dark matter models predict, large dark matter halos are not smooth, monolithic structures. They are assembled over time through the merging of smaller halos, and many of those smaller halos survive the merging process as distinct substructures orbiting within the larger halo. These subhalos, smaller concentrations of dark matter embedded within the larger halo of a galaxy like the Milky Way, are predicted to exist in large numbers, down to very small masses. Detecting these subhalos directly is extremely difficult, because most of them host too few stars to be visible as galaxies. But they leave subtle signatures. A small dark matter subhalo passing near a stream of stars, a stellar stream, the remnant of a disrupted globular cluster or dwarf galaxy, will disturb it, creating gaps or density variations that can be measured. Subhalos also affect the way gravitational lenses distort background images, producing small but detectable anomalies in lensed arcs and rings that careful analysis can attribute to dark matter substructure. These techniques are becoming more powerful as observational data improves, and subhalo studies are increasingly seen as a critical probe of the dark sector. The number, mass distribution, and density profiles of subhalos depend on the fundamental properties of dark matter, its mass, its self-interaction cross-section, whether it is truly cold or has some small residual thermal motion. Different dark matter models predict different subhalo populations, and comparing those predictions against observations of stellar stream perturbations and gravitational lens anomalies offers a path toward discriminating between them. It is painstaking work. The signals are subtle. The analysis is complex. But the scientific payoff, if a clear discrepancy or a clear confirmation emerges, would be substantial. What is striking, looking across all of these developments together, is how the field of dark matter research has entered a new phase of sophistication. The early decades were characterized by establishing the existence of dark matter, building the qualitative case, confirming it through multiple independent lines of evidence. That work is done. The existence is not in question. What is now being tested is the character of dark matter. Not just that it is there, but what it is like, how it is distributed at fine scales, whether it interacts with itself, whether the simplest model captures all of its behavior or whether reality is more complex. The tools available for these tests, Webb's extraordinary imaging, improved lensing analysis, stellar stream surveys, gravitational lens anomaly studies, are the sharpest yet brought to bear on these questions. And the answers are not all coming back clean. Not all coming back as straightforward confirmations of the simplest model. Some of them are pointing, gently but persistently, toward a richer picture. A dark matter that is not merely a passive, non-interacting scaffolding, but something with its own internal dynamics, its own behavior at different scales, possibly its own forces. Perhaps that is not so surprising. The visible universe, after all, is not simple. Ordinary matter interacts in a dizzying variety of ways, through gravity, electromagnetism, the weak force, the strong force, through chemistry and thermodynamics, and all the complexity that arises from these interactions at different scales. Why should the dark sector, which outweighs the visible universe by a factor of 5, be simpler? Maybe it is not. Maybe the invisible universe is as rich and varied as the one we can see, governed by its own forces, structured by its own physics, waiting for us to develop the means to read it in finer and finer detail. The maps are getting sharper. The probes are getting more sensitive. The questions are getting more precise. And the universe, as it always has, is taking its time answering, but the answers, when they come, are worth the wait. Science, at its most honest, is not a straight line toward the truth. It is something more like a conversation, sometimes confident, sometimes uncertain, occasionally doubling back on itself when the evidence demands it. The history of physics is full of models that worked beautifully until they didn't, frameworks that explained everything until something small and persistent refused to fit. Dark matter research is in one of those productive, uncomfortable moments right now. The large-scale successes of the cold dark matter model are real and substantial. The cosmic web, the clustering of galaxies, the acoustic peaks in the cosmic microwave background, these things are predicted with impressive accuracy by the standard framework. But at smaller scales, tensions have been accumulating. Not dramatic breaks, not sudden failures, but a slow gathering of observations that the simplest model handles less gracefully than cosmologists would like. Research has increasingly turned its focus to exactly these small-scale tensions. Not because the large-scale picture is wrong, but because the small scales are where the physics of dark matter's fundamental nature is most directly imprinted on observable structure. And what that focus is revealing is a growing list of places where the simplest assumptions may need to be revisited. A fresh analysis of distant galaxy clusters, systems that have long been considered among the strongholds of cold dark matter theory, has recently added to the unease. Galaxy clusters are the most massive gravitationally bound structures in the universe, and their properties have historically provided some of the strongest support for the standard model. But the new analysis found features in the distribution of dark matter within certain clusters, and in the statistics of cluster properties across larger samples, that do not align perfectly with the simplest cold dark matter predictions. The discrepancies are not enormous. They are not the kind of thing that makes headlines about physics being broken. But they are real. They are statistically significant, and they are prompting serious theoretical attention. The pattern, taken together with similar tensions at galaxy scales and the persistent cusp core problem in dwarf galaxies, is beginning to suggest something. Not that cold dark matter is wrong in some wholesale sense, but that the simplest version of it, the version with purely gravitational, non-interacting particles, may be missing something. That reality, as it so often does, is somewhat more complex than the first successful approximation. Then there is a stranger possibility, closer to home. Within the Milky Way itself, at the very center of our own galaxy, there is a region of intense gravitational activity. The supermassive black hole known as Sagittarius A star dominates the dynamics of the galactic core, its enormous mass governing the orbits of stars in its vicinity. The motions of those central stars have been measured in extraordinary detail over decades of observation, and they are generally consistent with the known mass of the black hole. But some researchers have raised an intriguing alternative. What if some of the apparent gravitational pull attributed to the central black hole is actually coming from a dense concentration of dark matter clustered at the galactic center? A compact dark matter clump, located at the very heart of the Milky Way, could in principle mimic some of the gravitational signatures currently attributed entirely to the black hole. The idea has a specific appeal beyond mere novelty. A dense central dark matter concentration might help explain a combination of observations that is otherwise somewhat awkward to account for simultaneously: the fast-moving stars close to the galactic center, whose orbits suggest a large concentrated mass, alongside the slower rotation observed in the outer parts of the galaxy, which follows a different profile. A model that invokes both a central black hole and a surrounding dark matter concentration can potentially fit both the inner and outer dynamics more naturally than either component alone. This remains a speculative idea. Separating the gravitational influence of a black hole from that of a surrounding dark matter distribution is technically very challenging, and the existing observations do not require the dark matter explanation. But it is the kind of hypothesis that can be tested with sufficiently precise observations of stellar motions in the galactic center, and those observations are becoming more detailed every year. What makes this period in dark matter research particularly rich is the diversity of alternative models now being seriously considered. Not fringe ideas or speculative fantasies, but carefully developed theoretical frameworks with specific predictions, motivated by real tensions in the observational data, and testable with the tools currently available or coming online in the near future. Self-interacting dark matter, already discussed in the context of the cusp core tension, has become one of the most actively studied alternatives to the purely collisionless picture. The core idea is straightforward: dark matter particles can scatter off each other through some force beyond gravity. The strength of this self-interaction, characterized by a cross-section, essentially a measure of how likely two dark matter particles are to interact when they pass near each other, determines how much the distribution of dark matter and halos differs from the standard prediction. If the self-interaction cross-section is small, the effects are subtle and mainly relevant in the densest environments, like galaxy cluster cores and the centers of dwarf galaxies. If it is larger, the effects are more widespread. The flexibility of the model, the ability to vary the cross-section and compare the resulting predictions against observations at different scales, has made it a productive framework for trying to simultaneously address multiple small-scale tensions. One of its most appealing features is that it can, in principle, explain why the standard model works well at some scales and less well at others. In large clusters, where the density and velocity of dark matter particles are high, self-interactions can isotropize the dark matter distribution, making the central structure more spherical and the density profile flatter in ways that match some cluster observations better than the collisionless model. In dwarf galaxies, the same self-interactions can soften the central density cusp. In large galaxies like the Milky Way, Where the dark matter density is lower and interactions are less frequent, the effects might be minimal, preserving the successes of the Standard Model in those environments. Whether this picture actually holds up across all observational constraints simultaneously is the subject of active and ongoing analysis. Some studies find that a particular self-interaction cross-section can explain several tensions at once. Others find that the same value creates problems elsewhere. The conversation is genuinely open, and the outcome will depend on the accumulation of more precise observations and more sophisticated simulations. Then there is a very different kind of alternative, one that departs from the particle scattering picture entirely and operates instead at the quantum mechanical level. Fuzzy dark matter proposes that dark matter consists of extraordinarily light particles, bosons with masses so tiny, perhaps around 10 to the power of minus 22 electron volts, that their quantum mechanical wave nature becomes significant at the scales of galaxies themselves. Ordinary quantum mechanics applies to particles at very small scales, atoms, electrons, the nuclei of atoms. But when a particle is light enough, its quantum wave function can be enormous. For a particle with a mass in the range fuzzy dark matter requires, the de Broglie wavelength, the scale at which quantum wave effects become important, could extend to thousands of light years. At those scales, dark matter would not behave like a collection of classical particles moving under gravity. It would behave like a quantum fluid, with wave-like interference patterns governing its distribution. In the cores of galaxies, fuzzy dark matter would form a solitonic core, a smooth, coherent quantum object with a definite minimum size set by the uncertainty principle. Density cusps would be impossible, because the uncertainty principle prevents the wave function from concentrating too sharply. This naturally resolves the cusp core tension without any need for self-interactions. The flatness of the central density profile is not a consequence of particle scattering but of fundamental quantum mechanics, the wave nature of the dark matter itself. Fuzzy dark matter also predicts interference patterns in the outer parts of dark matter halos, a granular, modeled texture in the density field rather than the smooth distribution the classical model predicts. These granules, sometimes called quantum granules or density fluctuations, could in principle leave observable signatures in the distribution of stars in dwarf galaxies, or in the properties of the intergalactic medium. Some tentative evidence for such features has been reported, though the statistical significance remains debated. The challenge for fuzzy dark matter is that the very lightness of the particles that makes them quantum mechanically interesting at galactic scales also makes them dangerous for the large-scale structure of the universe. Very light particles have significant thermal velocity and quantum pressure, which suppresses the formation of small-scale structures. Constraints from observations of the Lyman alpha forest, the pattern of hydrogen absorption in the spectra of distant quasars, which is sensitive to the distribution of matter at small scales, have been used to place limits on how light dark matter particles can be. Some analyses suggest that the mass range required for fuzzy dark matter to resolve the small-scale tensions may already be in tension with these large-scale constraints. Whether that tension can be reconciled within the fuzzy dark matter framework, or whether it represents a genuine problem for the model, is an active area of theoretical and observational work. Dissipative dark matter takes yet another approach, one that draws an explicit analogy with the behavior of ordinary matter. Ordinary baryonic matter can dissipate energy. Clouds of gas can radiate away heat, cool down, and collapse into denser structures. Stars, planets, and galaxies are all the result of this dissipation. If dark matter has some analogous ability, if it can interact with other dark matter in ways that allow it to lose energy and cool, then it might form structures that the purely collisionless model cannot produce. A dissipative dark matter sector might have its own version of atomic physics, its own analog of electromagnetic radiation, allowing dark matter to cool and condense within halos in ways that produce density distributions different from the standard picture. In extreme versions of this idea, dissipative dark matter might form dark disks, dark stars, or other compact structures embedded within ordinary galaxy disks, invisible to direct observation, but potentially detectable through their gravitational effects on stellar dynamics. The idea is speculative and faces significant observational constraints. Any dissipative dark matter component that forms a disk within the Milky Way, for example, would affect the motion of stars perpendicular to the galactic plane in measurable ways, and precision measurements of stellar kinematics have placed limits on how dense such a dark disk could be. But within those constraints, dissipative dark matter remains an interesting possibility, particularly as a component of a more complex dark sector in which different types of dark matter particles play different roles. Then there is sterile neutrino dark matter, perhaps the most minimal of the alternatives in the sense that sterile neutrinos are the most direct extension of known particle physics. Ordinary neutrinos are among the most peculiar particles in the Standard Model. They have almost no mass, interact only through the weak force and gravity, and pass through ordinary matter almost without trace. The Standard Model includes 3 types of neutrinos, each associated with a different charged lepton. Sterile neutrinos are hypothetical cousins of these, particles that interact even more weakly than ordinary neutrinos, having no Standard Model interactions at all except through mixing with their ordinary neutrino counterparts. Sterile neutrinos with masses in the keV range, thousands of times heavier than ordinary neutrinos, have been proposed as dark matter candidates. They would have been produced in the early universe through the mixing of ordinary and sterile neutrinos, and they would be stable on cosmological timescales. Importantly, they are testable. A sterile neutrino with a mass in the keV range can occasionally decay, producing a photon at a specific energy, half the sterile neutrino mass. This decay signal, if dark matter is made of sterile neutrinos, should be visible as a faint X-ray line in the spectra of objects with high dark matter density. In 2014, a tantalizing signal was reported, an unidentified X-ray line at an energy of approximately 3.5 keV, detected in observations of galaxy clusters and the Andromeda Galaxy. This was, and remains, one of the most discussed potential dark matter signals ever reported. The line was consistent with the decay of a sterile neutrino with a mass of about 7 keV. Subsequent observations with different telescopes and different targets produced a mixed picture, some confirming the line, others failing to detect it. The signal has neither been definitively confirmed nor definitively ruled out. The upcoming and current generation of X-ray telescopes, with greater sensitivity and spectral resolution than their predecessors, we'll be able to probe this question with considerably more power. If the 3.5 Kev line is real and truly associated with dark matter decay, the next generation of observations will likely make that case compelling. If it is not, the signal will fade into the background of astrophysical emission lines. Either way, sterile neutrino dark matter is a genuinely testable model, connected to known physics in a way that some more exotic proposals are not. It sits at the intersection of particle physics and astrophysics, offering both a theoretical motivation and an observational path to resolution. What is remarkable about this landscape, self-interacting dark matter, fuzzy dark matter, dissipative dark matter, sterile neutrinos, is that these are not merely names on a list. Each one represents a fully developed theoretical framework, with its own motivations, its own predictions, its own connections to broader questions in particle physics and cosmology. Each one has been tested against observations, constrained in some ways, supported in others, and remains a live possibility. The field is not confused. It is productive. The proliferation of alternatives does not reflect uncertainty about whether dark matter exists. That question is settled. It reflects the genuine difficulty of determining what dark matter is from the indirect evidence currently available, and the intellectual richness of a community willing to take seriously any idea that might move the answer closer. The conversation between theory and observation is ongoing, patient, and increasingly precise. And in that conversation, every new observation, every sharper map, every more sensitive detector, every more detailed study of stellar motions in a dwarf galaxy, is another exchange. Another question put to the universe, another opportunity for the universe to answer. The universe has been answering slowly. But it has been answering. There is a version of this story in which dark matter was always cold. In that version, the standard one, the one that has guided cosmological thinking for decades, dark matter particles were born slow. They emerged from the hot early universe already moving sluggishly compared to the speed of light, unable to travel far enough to smooth out the small density fluctuations that would eventually grow into galaxies and cosmic structure. Cold, in the language of cosmology, does not mean frigid in any everyday sense. It means that the particles had low velocities relative to light, that they behaved gravitationally like slow, heavy objects, that their thermal motion was negligible compared to the forces organizing them into structure. This cold beginning was not an arbitrary assumption. It made sense theoretically, it fit the large-scale observations, and it produced a universe that, in its broad outlines, looked remarkably like the one we actually inhabit. But a 2026 study has now raised a genuinely unsettling question about whether that cold beginning is the only possibility, or even the most natural one. The study proposed something that, at first glance, seems almost contradictory to everything the standard model assumes. What if dark matter did not begin cold at all? What if, in the earliest moments of the universe, dark matter was extraordinarily energetic, moving at or near the speed of light, a seething, relativistic component of the primordial cosmos, and only later, as the universe expanded and cooled, settled into the slow, gravitating behavior we attribute to it today? Hot dark matter is not a new concept in itself. For decades, models in which dark matter consists of fast-moving, light particles, particles like ordinary neutrinos, but more massive, have been studied and largely ruled out for the simple reason that they produce the wrong kind of universe. Hot dark matter would have streamed freely through the early cosmos, smoothing out exactly the density fluctuations that cold dark matter preserved. A universe dominated by hot dark matter would have formed its largest structures first and fragmented into smaller ones later, a top-down picture that contradicts the observed bottom-up assembly of cosmic structure, where small objects form first and merge into larger ones over time. What the 2026 study proposed is something more subtle and more interesting than simply reviving hot dark matter. It is the idea that dark matter might have had a hot beginning, a brief period of extreme energies in the very early universe, while still transitioning to effectively cold behavior before structure formation began in earnest. The mechanism proposed is connected to one of the most dramatic episodes in cosmic history, the reheating period after inflation. Inflation is the extraordinarily rapid expansion of the universe thought to have occurred in the first tiny fraction of a second after the Big Bang, an expansion so fast that quantum fluctuations were stretched to cosmic scales, seeding the density variations that would eventually grow into all the structure we observe. When inflation ended, the universe was in a cold, low-energy state, and the process of reheating converted the energy of the inflationary field into the hot plasma of particles that marks the beginning of the standard Big Bang picture. Reheating is not a smooth, gentle process. It is thought to be chaotic and violent, involving rapid oscillations of the inflaton field, parametric resonance, explosive particle production, and a complex cascade of energy that eventually thermalizes into the hot, dense plasma of the early universe. The details of reheating are poorly constrained. It happened so early, at such extreme energies, that observational probes of that epoch are extremely limited. The 2026 study argued that within this chaotic reheating period, dark matter could have been produced with extremely high energies, effectively relativistic, moving near the speed of light. This would represent a departure from the standard picture, in which dark matter is assumed to have been produced at rest or with only modest thermal velocities. But here is the key claim. If dark matter, produced hot during reheating, subsequently cooled sufficiently before the epoch of galaxy formation, then its initial energetic state might leave only subtle traces in the resulting large-scale structure, traces that the current generation of observations might not yet be sensitive enough to detect clearly, but that future observations might. The scenario also carries the intriguing implication that dark matter's properties at early times and at late times might be quite different. A hot beginning followed by a cold later epoch would require dark matter to have some mechanism for dissipating or transferring its initial energy, connecting, potentially, to ideas about self-interactions or to the behavior of particles in a dark sector with its own thermodynamic history. Whether this specific scenario is correct remains to be determined. Like many ideas at the frontier of early universe physics, it is difficult to test directly because the epoch it describes is so remote and so extreme. But it illustrates a broader point that the field is increasingly confronting. The simplest assumptions about dark matter's origins, that it was always cold, that its initial conditions were unremarkable, that its production history was straightforward, may not be the full story. the true history of dark matter could be more dynamic, more varied, and more connected to the specific details of inflationary and post-inflationary physics than the standard picture allows. This possibility has implications for the theoretical models scientists will need to construct going forward. A model that describes dark matter as purely cold from its inception is simpler and easier to work with. A model that must account for both a hot beginning and a cooler later universe, and that must correctly predict how the transition between those two states occurred, and what observable signatures it left behind, is considerably more complex. But if the universe demands that complexity, the models will need to provide it. That, in many ways, is a summary of where dark matter research stands at this particular moment. Across all the fronts, small-scale tensions, alternative models, questions about self-interaction and quantum wave effects, the new possibilities raised by studies of reheating, what the evidence is consistently demanding is more complexity than the simplest assumptions provide. And yet the simplest model, for all its tensions, has not been decisively overturned. In at least one recent careful analysis comparing cold dark matter against several of its proposed alternatives, the standard model still fit the full range of observations better than any single alternative. Not perfectly, not without tensions, but better than the alternatives individually offered. This is a reminder that tensions in a model are not the same as a refutation of that model. A model can be imperfect, can have open questions, can fail to fit every observation with equal grace, and still be the best available description of reality. What the modern observations are doing, gradually and collectively, is pushing scientists toward richer models than before. Models that might incorporate a moderate degree of self-interaction alongside the basic cold-dark matter framework. Models that might allow for a more complex production history. Models that might involve more than one component, with different properties and different roles. The destination is not a wholesale abandonment of the decades of successful cosmological modeling. It is an extension of it, an elaboration, driven by the improving precision of observation. The modified gravity alternative deserves mention here as well, because it represents the most radical departure from the dark matter framework and continues to attract serious attention from at least some corners of the research community. Modified gravity theories, of which modified Newtonian dynamics, is the oldest and best-known example, propose that the anomalies attributed to dark matter are not due to unseen matter at all, but to a modification of the laws of gravity at low accelerations. In the Mond picture, below a certain threshold of gravitational acceleration, the effective strength of gravity is enhanced relative to what Newton and Einstein predict, producing the flat rotation curves and other gravitational anomalies without invoking any additional mass. Mond works surprisingly well at the scale of individual galaxies. Its predictions for rotation curves match observations with a precision that is sometimes difficult to explain within the dark matter framework. And there are relativistic extensions of the basic Mond idea, most notably TeVis, tensor vector scalar gravity, and more recently covariant formulations, that attempt to provide a full cosmological framework comparable to general relativity plus dark matter. But modified gravity struggles badly with certain observations. The bullet cluster, discussed earlier in this story, is particularly challenging. In a modified gravity framework without dark matter, the mass should follow the gas, because gas is where most of the ordinary matter is. The observation that the mass follows the collisionless stars and dark matter halos, not the gas, is very difficult to explain without invoking actual additional dark matter. The cosmic microwave background also poses problems. The detailed pattern of temperature fluctuations in the microwave background is sensitive to the amount of matter, and it fits beautifully with a dark matter component. Reproducing the same pattern within a modified gravity framework without dark matter requires considerable theoretical effort and does not achieve the same clean fit. In recent careful comparative analyses, cold dark matter, even with its tensions, has come out ahead of modified gravity alternatives in terms of overall fit to the full body of evidence. The question is genuinely open in the philosophical sense that no alternative has been absolutely ruled out, but the weight of evidence continues to favor the existence of real additional matter over a modification of gravitational physics. Most researchers in the field proceed on the assumption that dark matter is real, while remaining appropriately open to the possibility that the gravitational framework might need adjustment in some respect. These positions are not mutually exclusive. The universe may contain both dark matter and modifications to gravity at some level, just as general relativity contains both matter and the curvature of spacetime as distinct components of the physical picture. What is clear, standing at this moment in the history of the field, is that the era of simple, clean answers has given way to something more demanding and more rewarding. The questions have sharpened. The observations have deepened. The theoretical landscape has broadened, and the search itself is transforming. The most recent dark matter mapping work, the web-based surveys, the weak lensing analyses reaching back 10 billion years, the high-resolution maps of previously unseen structure, represents something more than an incremental improvement in detection capability. It represents a shift in the fundamental nature of what the field is doing. The project is no longer simply trying to confirm that dark matter exists or to catch a particle in a detector. It is becoming something larger and more systematic, a detailed measurement of dark matter's structure, density, and evolution across cosmic history. This is a different kind of science from the early decades of dark matter research. Not more exciting, perhaps, but more mature. More precise. More capable of distinguishing between models, testing assumptions, and mapping out a territory that was, not long ago, completely invisible to human knowledge. The field is moving, in the words of some of its practitioners, from hunting to surveying. From the single decisive moment of discovery to the long, careful work of characterization. From asking whether dark matter is there to asking what it is, how it behaves, how it has changed over time, and what it tells us about the fundamental nature of matter and the universe. That work is well underway. And it has only just begun.